So here we have it. Really a frequency graph. I think the order is incorrect because I do the frequency first, a polygon, and then when you divide by little n, you turn them into probabilities and they become histograms. So another way of calling this thing is that this histogram right here, I've been calling sample distribution. Okay? And this frequency polygon is really just a graph of tallies. These are called tallies. Let's fail in this cell, this meaningful in this cell, and so on. And then you just build a box according to how many units there are. You know, that's a polygon. And the Ogives is a cumulative process. I'll show you. Okay, so let's just go through that, make sure everybody's on the same page. And, so this is all about organizing data. And frequency distribution is just, first of all, where did you get your data from?
The population.
The population. You took a random sample, right? Now you want to look at how they're piling up, how they distribute. So we have a frequency distribution. It's a lot like the histogram. Let's see. Okay, this is called categorical. As you can see, it's not numeric, it's alphabetic. So, but even so, you can count how many of each. So this is a frequency graph. This is a tally. If you put it on the side, you know, like this way, it starts to look like, you know, polygon. A polygon frequency. So, you know, this is the percentage of the time it happens. This is 5, and you know, what is little n? Well, it's how many tallies there are. That was each an observation that we took, and we want to know, and we grabbed one observation, right? We said, is this an A, B, 0, oh, these are blood type, right? And so, okay, that person was a type A. Then, next person I grabbed from our sample that we got from the population, click, 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 and in the end, the majority of people, 36% were type O from our sample. You understand what that little line means? It means it's one of these guys. So here's A, then B. So you make a line for A, and make another one B, and then B again, and A again, and O again, until you found a place for all of them. It's not hard. It just, you know, you just count how many A's there are, how many B's, O's, and B. Now if you turn it this way, you got a frequency graph right here. Because you can put an axis like this if you want to turn around, right? And then have this be 5, this one's going to be 7, this is going to be 9, this is going to be 4, and like that. So if I turn it this way, and it starts to give me what the distribution of the population is like. That's a whole field in itself. I've taken a class that's just about probability density functions. And deriving some testing to see if they are. Okay, so let's go. And then, let's see, did I get this right? Yeah. Okay, so now, if I give you a graph where you see all the tallies, but you didn't actually have the numbers from the data that we got from the population. If I give it to you already grouped up, we call it group. So if I give you something like this on a question, and you split it up into classes, and you see how many they fall in here. Let's say, right? If I give it to you at this format, say this is 0 to 5, 5 to 10, 10 to 15, whatever. The point is that these tallies, if you take a look at it, they're simply the counts, right, of what fell in each one of those cells. So, but if I give it to you like this, without the raw data, then you don't really know what this data point represents. You only know that that's something that fell between 0 and 5. Now, it's unusual. Normally you get the data from the population, but they do have a way to calculate the mean and the standard deviation from group data. You should learn it. Okay. So, this is the smallest and largest possible data value sets in a class, lower and upper class limits and class boundaries. This is, to me, a form of accounting, like putting things in the right. Okay. Okay, so here, to find a class boundary, the average of the upper class limits of one class and the lower class limits of the next class. So let's show you. Okay, rules for classes and group frequency distribution. Anywhere from, this is kind of like the art part, anywhere from 5 to 20 classes. Class width should be an odd number. Well, that's nice. The width, I don't know, I'm not sure why. The classes must be mutually exclusive. That means, what does mutually exclusive mean, anyway? When two events are mutually exclusive, what does it mean? They're what? Exclusive. That's good. That means one doesn't affect the other. So if you've seen, like, I know you've seen events. So if you have like this, and you have an event A occurring and an event B, as it's drawn here, A is mutually exclusive to B. If you have an intersection, then it's not the case. They're not. They're not mutually exclusive. Okay, so when you do your boundaries, right, what they're saying is that this class shouldn't overlap with the other class. That means they're not mutually exclusive, right? You don't want to have any overlap. That's all it means. The classes must be continuous. That means it goes from the lowest data point to the highest. Exhaustive means there must be a place for everybody. And you want the classes to be equal width, right? Okay. Any questions? And then we have, great. That was a record.
Statistically, you should give up on your computer.
Yeah, I'm thinking.
Be two more.
I need somebody to fix it. What it says here, okay. So we're going to construct a line from the lowest data point to the highest data point. And then we'll have these same width on the class, and then we'll just see where they fall. Stack crunch can probably do it too once you learn how to finesse it. So if that's the case, so simply you take the highest and minus, and this is the range. If you do this, you know you're going to get every observation in there, right? Because it's going from the lowest to the highest. And remember, we wanted 7. So 34 divided, by 7 is 5. So we want to make 7 classes 5 wide. It says round up if there's a remainder. Okay, that's always the. All right, so for convenience, we'll choose the lowest data, 100. So 100. Right, 104, 105. The first upper class is less than the next lower class. 105, 110. You see what's going on here? That's 5. 110, 115, 120. You see? And then, so it says the first upper class is 1 is less than the next lower class. The subsequent upper class limits are found by adding the width to the previous upper class limits. So that's that little fudge factor we want so that we don't, let's see. Okay. So this is the most common graph in research. I would have changed the order. I would have put this first. Because normally you're going to construct a frequency polygon before you start doing a histogram. See what I'm saying is that if you had a very basic, let's say you had three cells, okay, and then you have some data that's following those 3 cells. So if I have 2 here and 5 here, and maybe 1 here, that's really a frequency. What makes it a frequency polygon is I put this, and I call that 1, 2, 3, 4, and 5. See? So then this is a polygon right there. And this would go up to 5, you see? And this would go up to 1, let's say, for example, right? That's the frequency polygon. But if you figure out your sample size, little n, okay, so this is, let's say this is, there's 1 here, 1, 2, 3, 4, and 5. Okay? So if I take n, which in this case is how many observations? We have 5, and then we have 2 and 1. So that's 3 and 5, so we have 8, correct? So if I take these same numbers, you see the 2, meaning that it has a height of 2, and I divide by 8, you suddenly convert it into a histogram. Because this scale is changing to probabilities. So every one of these numbers, 5 divided by 8, right? So this, the probability that I turn the lights off and I grab somebody and they fall in this is going to be 2/8, which can simplify to 1/4, which can be 0.25, which can be a 25% chance. Because, and this guy, I had 5 in there, right? So I had 5/8. And over here I have 1/8, right? And if you notice, to be a proper distribution, these better add up to 100%. In other words, 2/8 plus 5/8 plus 1/8 better equal 8/8, because it has room for every single observation, 100% if you add them all up. So do you see how I change from a frequency to a histogram? It's just dividing the same scale by little n. Then I can call these percentages or probabilities that I grab somebody. What's the likelihood of falling here? Well, they have the best likelihood of falling here. Or I can say, what's the likelihood of falling between here and here? And that would be the summation of those two. Okay? Yeah? Remind me to take roll. I gotta put it on the computer this time. Okay. Any questions? Is it too easy? Okay. And then I go, let me clear that up. Okay, now we're going to go to the histogram. Okay, so this is back again. Now here's how they seal up the gap. 104, see, 0.5 and 104.5. So now it's continuous. See, from 99, you went 99.5, and then you went 104.5. And then you started at 4.5, and then you went 109 plus 5. So we're adding a 0.5. We're actually subtracting a 0.5 from this side, you see? And we're adding a 0.5 on this side. This will help that we don't get any ties. Because if you notice, none of the data has decimal point in it. So it's not going to land on any one of these points. So we have, you see what I did? I made it a little wider by subtracting 0.5, that's 99.5. I made it a little wider to the right by 0.5, see? Now if it's already a small number, you can use 0.05, it doesn't really matter. Okay, 105 to 109, see that? You understand? And then we went and did how many fell in each cell. So this would be really, we're still talking about frequency, we haven't hit histogram yet. Okay. Now, notice that this is a frequency, and as I use histogram, my histogram, the way I explain it, has probabilities, not, this is like a frequency gram, I call it, because it's just frequencies. This right here, 3 of them fell in here, 9 of them fell in here, 18, see? There's really, I call this a relative frequency graph. But anyway, that's the layout. You can see this one, positive autonomous is somewhat bell curve, right? And so this is histogram frequency polygon. Okay, so so here we have class midpoints that are represented on the horizontal axis. So let's see. That's the temperature one. Okay. So this particular frequency polygon, what they did is they just they put these points on the edge and made this. It's a frequency polygon. I don't use it much, but I guess anybody can use it. I prefer the other one, but it's okay. So here are the temperatures. Here are the frequency. You see at the points 102, 107, and then this Ogive is a cumulative, so let me show you. It represents, okay, this is the same one for the temperature, the Ogive. This is a cumulative frequency. So what that means is that what you're going to do, that's 2, but then you're going to accumulate. You're going to 2 plus the 8 is 10. Then, right? And now we have 10 plus 18 is 28. And 28 plus 13, you see? It's accumulating. Instead of starting over, it's taking that value and adding it to the latest value. So if you graph an Ogive, it will never go down. It will go like this, because the first one, let's say, goes up to 2, and the other one goes up to 10. And what it'll do, it'll start getting less and less steep, but it'll never come down because it's adding. It's cumulative. Okay? Let me think out. Anybody? There it is. So you can see what's happening. Remember 5, 10, it's accumulating. Notice how it goes up the steepest is when it's growing fastest, but this will never come down because from now on we'll just be adding more and more, but it'll be maybe at most getting a little bit more flat. But it will never come down because we're adding the previous data, the previous frequencies. This is the cumulative frequency. Okay, so constructing statistical graph. You got a suitable scale, depending on how wide your range is, and plot the points, draw the bars. So, frequency distribution. So construct a histogram, a frequency polygon, Ogive using relative frequency for the distribution. So here's the data. Next time you come into it, instead of tallies, you put numbers. Might be a better way. Okay, and then there's the upper boundaries. Now, relative frequencies. Do you see this? These things right here? Do you notice how they're different numbers now? These are probabilities. They took the sample size. If that had a, before we had a, what do we have here? We had 1, right? But the sum of our tallies is 20. That is our sample size. The summation of our frequencies, the summations of these is 20, right? So, look what happened. I took 1. Do you remember when I had my histogram and I did it like that and I said, you just take any one of these, any relative frequency graph, and if this went up 1, and this went up 3, and this went up 5, and then 3 again, let's say. So this is your scale, because it's just counting frequencies. So it's 1, 2, right, and we'll call that 3, we'll call this 4, right, and then back. Oh.
Where'd you go?
It's a good thing I looked over, because I would have been sitting there looking at the blue board. Oh, there you are. I thought you took a break or something. You like sitting over there?
Yeah, I could do more people.
I do this pattern here. Okay, so all I did is take this scale. What is this scale? This scale. You know, a 1, a 2, a 3, a 4, a 5, right? And I take each one of them and divide by the sample size. Now they became probabilities. Now this is a histogram, not a frequency gram. So they got this other thing called frequency polygons, but that's the points that you put. But this is just a frequency graph, and then divide the scale here, whatever these numbers are, divide by, in this case, 20. You see? So what is the probability that I grab something from that sample and they fall between here and here? It's going to be 5% chance. Now, we're just going to graph it. The graph is just like this, except I just change these numbers now to probability. Oops.
Caveman's coming out.
I wonder if I throw something. Okay.
Happy I actually memorized your password, or we'd be here
Look at
for
that.
a very long time.
You see, instead of 1, did you say something?
Yeah, I said be happy I memorized your password, or we'd be here a very long time.
Okay, now, before we had 1 observation, yes? But this is 1 divided by 20. Before we had 2, I believe, right? And now, because I'm dividing by 20, the scale changed, that's all. Anybody know what I'm talking about?
I get it.
Okay, I got 1.
I get it.
All right, 2. Anyone else?
I don't know what you're talking about.
Well, first you gotta count how many things fall in here. So this scale is a count. 2 fell in here, 5, whatever. So you just go 1, 2, 3, 4. It's how many counts. But when you take those same counts, 1 tally fell in, and you divide it by how many there were, 20, it becomes a probability. Right? So there's a 5% chance, that's 1 divided by 20, that whoever I grab, not looking, will fall in the cell. It's whatever this height is before, what was it? Okay, let's do the scale here. Right. And this is exactly the difference between the histogram and the frequency graph. It's that in the frequency graph, we would have 1, 2, 3, 4, and 5. This scale is the same scale, except we took every one of these and divided by 20. And now this is the axis. If you don't look at this, what do you got? Frequency graph. You're going to hide this, you got the histogram. That's all. Okay? Anybody? No? Okay, we'll try. Let's see. Okay, so first, following frequency distribution of miles per week, about 20 runners. So we got these runners. They're our sample. But this is already grouped. So now what I got a midpoint. You see? A midpoint, midpoint, midpoint. This is class midpoints. And this is what we had before, like 8, for example, divided by, what's our sample size here? Well, you'd have to add them up. But if you take every one of these and divide by total, you're going to get these probabilities. Okay, and then this is an Ogive. It's like you see, it's like cumulative.
Yeah.
So it's adding that to what it was before. I think it was 0.10. So now we have 0.15, and that'll be added to 0.15, 0.3. You see, it's just adding up. So let's show you this. And there it is. This was the first one, but the next probability you add to this one to get that one. And the next one you keep accumulating by adding on top of the previous probability. All right? And so where should this start to approach? Well, 1. Right? Because you add them all up, it should start approaching almost 1. Okay, so let's look at the different distributions. We call that the bell, which is the normal distribution, the uniform, the reverse J, and J shape. Okay. Whatever name you want to call it, it's okay for me. This is just a bar graph. Just, right? It's what you saw. How many of a card? It's not even, I don't know why I have it. Another type of Pareto chart. A Pareto chart is just organized from highest to smallest. You notice how it's stepping down? It will always be that way because you're going to resort things. See, auto plus. Remember auto is highest? Does anybody remember that? And so that goes first. You see, these are frequencies, not probabilities. A probability has to be less than 1, you remember? A fundamental thing of probability, of a certain, of a value of x, some random variable that's going to be loading up with some kind of distribution, has to be less than or equal to 1, but greater than or equal to 0. That means it can equal 1 and it can equal 0 included. But if you got any number and you come and you might know it's right, and I see that that probability is greater than 1, I already know you're wrong. You can't have probability 3. So this is just another kind of graph. Dot product, dot plot. There it is. No, not dot,
Dot plots on this class?
There was some on the homework, yeah.
So what?
The dot plots.
Oh, yeah, dot plots, yeah, but I misspoke, I was talking about the term in physics.
Oh,
Yeah, dot product is multiplying matrices, right?
Yeah.
Dot
that-
product is a shit show and I hate it.
If you get to calculus, you learn about dot
What
product.
kind of English is that? Shit show in my head.
I failed at dot product.
Okay, let's try it. Now patient testing center. Number of diagrams formed 20 each day.
There, Michael.
So they want a stem and leaf. Stem and leaf is where you can put one digit along this axis and the other like this. Okay, so you can see right here, you see number 13? I just put the first, the tens unit here, and then the ones unit. I don't know anything about it either. I think the other ones are just as easy, but anyway, is that it? Yeah. Any questions? They're really just organizing data. I don't like exactly the order they do it. I would do the frequency graph and then the histogram. Got a lot of different names. Okay, so let's go back here. Yeah. Let's see. How do I get back to the main screen? Right here. Okay, I don't see it. Is there a? Can't really. There. Okay. Now, okay, so now, chapter 3. Okay. These we've been going over. What's another word for a measure of central tendency? Okay, you got an X bar, which means average, which means mean. Another way of saying it. Man, my handling. Okay, and that would be for the sample side, right? On the population side, we have mu, the parameter. Okay, and then measure variation. Well, you know, S. And you know that's going to predict lowercase sigma. Where this is the sample, deviation, or variance, right? And this is the population deviation. The difference between variance and deviation is squared. If I have S squared, that's a variance, or variation. If it's just this, right, we talk about it, this deviation. It's really the same number squared, so don't freak out. Variation is the same as, you know, what we've been looking at as deviation. All right, and then measure of positions. Okay, and explore, and then we do the analysis. So let's try that. Why don't we? Okay, so let's see what we got here. So we have average, variation, and position. It's not like physics, huh? Okay, measure of central tendencies. The average, the mean. Do you remember the median? When we drew like lines like this? You know, the mode, the mid-range. What is the weighted mean? Anybody? Do we know what a weighted mean? By the word itself? It would be something like, suppose you want to calculate your grade, and or I'm going to assign a grade, and I say, well, that was your first grade, this is your second, and your third. However, I'm going to weight this by a factor of 10, and then I'm going to add up my weights. You see, you're just weighting one value more than the other, or reducing. Okay. Okay, now look at the word a statistic, right? Those things, do you remember on the sample side? X bar, S, I didn't put it there, but we have a P hat. Do you remember proportion? All of these on the sample side, each one is a statistic. They're called sample statistics. Okay? And on the population side, remember, we have mu, sigma, we have true P. Do you recall? All of that on the population side, instead of calling them a statistic, they're a parameter. That's what we seek out over the God's known. Okay? I've done that over and over. But you have to know, as a group, on the population side, the group of all of those are the parameters. And the group of the statistics are the sample statistics on the sample side. Sometimes, okay, I always hate this because this, you know, it's rounding up. I'm not real picky about it. This is rounding up should not be done until the final answer is calculated. Okay. Do we know what X bar means? We do. It's x1 sub 2, x2 sub 2 to xn, which is written mathematically as a summation. Now I have here I equals 1 to the n, more detailed. I don't know why they do that, but okay. And then this is X bar, correct? And look at that. Do you see that's a little n? That's the size of our sample, you understand? But look at this, mu. That's a parameter. This is statistic. Mu. Add them all up, look at that. Until you get to capital Xn. X sub n divided by capital N, right? They're unique. I mean, they're almost the same. Except this is a subset of this. If we could do this directly, we wouldn't even need to have a sample. Right? If we could go right into the population, calculate the average. All right, that's average. There you add up all your data points, divide by how many were there. Guess how many? 9 observations. Yes? Yes? Okay, and there's a number freak out. This is how you're going to calculate the average if I give you group data. Because you don't know what the raw data is. You only know that a certain amount of that raw data is following each cell. Yeah? Yes or no?
Yes.
Okay. So how do I find, how do I find my average? Well, we're gonna pinch it by instead we're gonna look at the midpoints of every class. You see this? That's the midpoint of every class. And that's going to be our new x. And then the multiple frequency by the midpoints of each. So it looks like this. Right? So let's see. So now x bar. So now let me write it in my fashion where x bar will be equal to the summation. Our count now be careful because I equals 1, correct? But it's not going to go up to little n, it's going to go up to the number of classes. Because remember, this is a substitute for the real data. Okay? So we're going to get every frequency in every, see the I?
Don't blame me.
This forces a little break. I can release. I'll just wait here.
It's good to give your mind time to
Yeah, that's right.
digest
It's like a
material.
forced break. Okay. Now this goes to the number of classes, yeah? Okay. Yes?
Yeah.
No. So remember, if I have the first cell, the second cell, the third cell, the fourth cell, the frequency that fell in this particular first cell is F1. That would be like, I'm not saying what it's worth, I'm saying the number of counts is F1. This is going to be F2. This is going to be F3, and this is F4, right? So let me see that. Yeah. That's how many, okay, that's all that is. So when I put 1 into the I, I'm talking about this first cell. Here it is. Well, we didn't expand it. See it? And then this is X sub M sub I. No matter if figure out. Because we're going to have how many midpoints? Where the number of classes is 4, you see? Not little n, but 4. Because you don't have the extrapolated, you don't have the actual raw data. And then we're going to take, this is a new way of calculating x bar when the data is grouped. Let's try it. Okay. You see this? Is this raw data or grouped? Grouped. You don't know what the raw data is. All you know is that one observation fell between 5.5 and 10.5. So am I asking you to find the average and you don't have the raw data? You have to use a different formula. So what I'm saying that formula is that it's simply this. When we expand it, the expanded version, you'll see that it's easy. The expanded version is that I'm going to take my first frequency, F1, right? And this is for calculating x bar on group data. And I'm going to multiply it by my first midpoint of that cell, plus F2, you see, times the midpoint of the second cell, plus dot, 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 to wherever we're going to end, right? And that's going to be F of X of M and number of cells. That's, no, it looks ugly. But this is going to be times, yeah, the frequency in M. That divided by N. And what is N? N is simply the sum of all your frequencies, F of I equals 1 net little n. That's that. That is N. So, what would it look like? Look how easy it is. It's just x bar. Once you get the hang of it, it's simply going to be how many frequencies fell in the first cell? Yes, 1, right? And then what is its midpoint? So that's going to be from 5.5 to 10.5. So if it was 5 to 10, right, it would be 7.5, wouldn't it? So would you say 8? Okay, so I got 1 times its midpoint, 8. plus, how many fell in the next one? F of 2. Yeah. And what is its midpoint? Well, it's going to be like 5 more than that, isn't it? Should be 13. Plus, the next one, how many fell in? Yes. And its midpoint?
23.
So you added 5, what did you add? 8 to 13?
17.
5 to 13, 18? Or was this new math or what? I don't know. This is times.
I was looking ahead of next.
Oh, you're way ahead of me. Okay, so how many fell in the next?
5.
5. And what is its midpoint?
That's 23.
That's going to be, I just adding 5 to the last midpoint. Yeah, plus, next one,
4.
yeah, times 28, plus 3, times midpoint, plus, how many? Times 37. And I divide all of that by the total number of observations. That's how we're going to finish it. It's not perfect, but it's not bad. We're using midpoints as our like a new X. Okay, let's take a look. Let's see. All right, so here exactly what we did. It was 1, right? Sometimes the tables might help you line it up. And these are the midpoints. And these are the products. This is a summation of adding the frequency and its midpoints. And so we're going to take 490 and divide by 12. That's our new average. That's what we're using as our average from group data. I wouldn't expect it to be exactly like it was from the raw data, but it'd be close. I think relatively close. You understand what I'm saying? Okay. We went through the median. Do you know that, or do you want us to get it again? Okay, I guess you're not. Let's see. Median's when you line them up. You remember the first quartile, second quartile. So here it is. All I've done is put it in order from lowest to highest. So that what I have is I do geometry now. This has to be the same length as this one. So that is called our second quartile, which is also equal to our median. Okay? And if you did that game again, but you do it this way, it's like another little geometric thing, so that this distance is the same as that. That's going to be your first quartile. And likewise here, we're going to go 2 units, and 2 units. Right? This will be my third quartile. Now, what can we do with that? Well, it turns out that, we got these outliers. So basically we can construct a box of Mr. graph from it. I'm not sure if it's out of place here now. Okay, so now, if you look at this, you got 3 and 3, 6, so we have 8 data points, right? When you have 8 data points, we have a problem getting to the middle, because to do the geometry, the distance of this guy from here, and distance here, so we have this gap. So you just take the average of this plus that, divide by 2. This is all more number of tornadoes. Find the average of the 2 middle values. Oh, that's what they did, right? Because the median would go like this and there it is again. I don't know why. What happened? The mode is which observations repeated the most? The highest one would be mode. Okay, sine, what is this? See the 3 tens? Your mode. Lauren, for me.
If there's multiple modes, are they just all modes?
Oh, is there?
If there's like
We have here 5?
4 or 5 sets of the same amount as a number of modes, are they all modes?
You beat if I had 3 sets of 10 and 3 sets of 20 and 3 sets of that. Just flip the coins. It'll make it probabilistic. I don't know that, I mean, you want to look at it, but I'm not sure you can color up too much. There, 104. And these two, so the data set is to be bimodal. And if you have more, try modal.
Alright, so they're all modes.
Can't go wrong. Okay. Now, area boat registration. 6 counties in Pennsylvania, and these are registrations for boats. Since the category with the highest frequency, oh, that's boring. That's just mode. Okay. Mid-range. It's the lowest and the highest divided by 2. Boring. Bank figures. So, this is our smallest, this is our biggest. Take the average. Okay. Weighted average. Okay. So, look, A is weighted by 4 points, 3 by 2, 4 by 3. You see? So, when I took the first one, I got 3, and my credit's right, but my weight could be 4. And then, or let's say 3 is the weight, and 4 is the data point. 3 and 2, and 4 and 3, and 2 and 1, divided by the sum of the weights. Add those up. And there's the 12. Sometimes you might want to do a weighted average. Certainly if I give tests, I could count some quizzes worth more than others. If I start to weight them, then I have to divide by the total amount of weights that I've used. It just takes a little practice. It's not hard, I don't think. Okay, now we're going to talk about properties of the mean. You know, it's the average is used for. We're going to use it to make estimates and inferences on mu. It's all one. Properties of mode, I don't really care. Mid-range. So, look, here's the mode. Here's the median, and here's the mean. If you notice, this thing's not symmetric, is it? What I mean is there's more graph going down here than here. Yes? So if we had the mean, mode, and all line up, look at it, it's symmetric about this axis. I could fold it up. So it does mean something if they all line up. Okay, this too didn't, it was like this, mode, median, and mean. So now it's skewed to the right, skewed to the left. It's just definition of terms. I don't know what else they want. You do know the range, right? The range is the highest minus the lowest. I'm not sure why they're doing that now here. So 2 brands of outdoor paint. Find the mean. Find the mean and the range of each group. Oh, the range is easy enough, right? It's going to be the smallest data point minus the largest. And then this one's going to be the smallest, right, minus the largest, right? But the average, we can just add them up and divide by how many there are. That's That's average. No harder than that. Okay, this is what we do from I equals 1 to n. That means you add all these up and divide by capital N for mu, and you're going to take the range is here. So here, if this is the whole, not the sample, but the actual population, it's kind of confusing. I don't know why they do that, because rarely you would have it, mu. But anyway, it goes to capital N, right? And there's our range. That's easy. Okay, so the average for both brands is the same, see it? The average. But if you take a look at the range, it says brand A has a much greater than the range of B. So which one would you buy? Would you get the one that has the smallest range, or the one that has the widest range? These here are what do these numbers represent? It represents, see how long each will last before fading. So I guess they're in months. So now that you know that, you want one that has a wider, you want one with wider range or smaller? When we're talking about how long the paint lasts before it fades.
Smaller.
You say smaller, how do you explain that?
Well, you want your paint to last long, so.
So you want the smallest ones, or you want one that's the widest? Let's see. Oh, didn't say. It said which brand? I'll leave it to you. Okay, now what we're going to talk about. We finished the average, so now the standard sample deviation. And what do we call the sample deviation over on the population side?
Population deviation?
Yeah. That's how easy it is. That just change the word sample to population. Okay, and then we have the standard deviation, remember, is a square root. So all they're saying is that solid fluid S is equal to the square root of S squared. And I have two copies of X. This is looking for packages of two that come out. Are you with me? That's the distance. So if you see an S squared, we call it variance. It's the same number, but if you see S, that means we took the square root of it. We call that a deviation. Okay? Nothing to sweat about it, just what format you want it in. So we have a population variance, that's the population, and we have a standard deviation, it's a square root. Okay. Okay. So remember what I said variation is, or deviation? It's how the data is spreading away from its average. Right? So determine the number of data values that fall within a specific interval. This is Chevyshev's theorem. Russians are big in probability theory. And this is Russian. And we'll be talking about the Chevyshev here. Okay, this we've done many times. That's lowercase sigma that we call the population deviation. No, not the this is the population. Well, it's got mu in it, so this is all about the population. I don't know how it does it, but normally we'd have X barred it because we were doing the sample. But this is assuming that you do it, so we call that, right? That is the average from every data point. I equals 1 to capital N. And so, do you see the difference between here and here? Do you see that square? You see the two copies? That's a variance. No copies, just one copy. That's got a square root, and that's called a deviation. Right? No. You don't see it?
See it?
Yeah, but you grasp it. If there's a square, it's a variance. If there's no square, there's better be a square root somewhere, and that's called a deviation. Same number, just square or square root. Okay. So first, we find the average, and they're talking about as though we could get on the population. So let's suppose you have mu. Then, you're gonna take mu from every single observation in the population. Some of them can come out negative, so you square it. Then you add the sum of those, and then the sum of squares, and then, how come they don't show the rest of it? That's weird. Okay, so watch. I can just as well change mu to x bar if I'm talking about the sample. So here is it months. And then we took this average, the average of this. Do you remember? In when we were doing S, let's see. When we were doing S, from the sample deviation, we were taking the summation of every observation x of I and subtracting its average, x bar. And because some could be negative, we square it so we don't run into that problem. And then we divide by n minus 1 square root. That's going to be exactly this sort of thing, except we replace x bar with mu. And we don't go up to I equals 1 up to little n, we'd be going up to capital N, because we're in the population. So you can see that it looks just like it. This is the population deviation, right? And that was going to sum from I equals 1 to capital N. Now I have x of I, but in the population, we don't call it x bar, we call it mu. And that too is going to be divided in this case because it's a population. That should be capital N, shouldn't it? So, error. Alright. So, this was squared, you see? And this is that. And this is that. Now, to get rid of that square, I have to square root both sides. The square root of a square is just a number. Okay? Let's go over a practice for square roots. I know that you've seen it, but let me cover it because some of you might be rusty. Is that okay? All right. So, all right. So what I want you to know is that the fundamental theorem of arithmetic, you know, it's the fundamental theorem of arithmetic. Okay, and it simply says that every natural number, the set of natural numbers, would be the set containing 1, comma, 2, comma, 3, comma, dot, 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 to infinity. It's your natural number. You count your fingers and your toes, count, okay? That's called a set of natural numbers. Natural numbers. All right? Now, that set has some interesting subset, and we call the prime numbers. And it's simply numbers, a set that can only be multiplied by itself and 1. So in other words, the only way to get 1 would be 1 times 1. There's no other way. So we consider that a prime number. 2, the only way to get 2 is 1 times 2, and that's 2. And that'll be the only even prime number. Okay, so prime, the set of prime numbers. Okay, now, 3, also 1 times 3, no other way, but not 4. 4 is 1 times 4, right? But you can also do 2 times 2, so it is not prime. Okay, how about 5? Prime or not prime?
No.
Well, how many ways can you write 5? 1 times 5, can you write it another way?
No.
Prime. 6?
6 times 1, 6 times 2.
Not prime. 7?
Prime.
Only one way. 8?
No.
Not prime.
9?
Not
No.
prime.
10?
No.
11?
Prime.
12?
Not prime.
13?
Prime.
14?
Not prime.
15?
Not prime.
16?
Not prime.
17,
Nine.
18,
Nothing.
19,
Nine.
20,
Nothing.
21,
Nothing.
22, 22,
Nothing.
23,
Nothing.
23, not right?
Sorry, my bad.
Okay. So here's the weird thing about these numbers, because they're clustered weird, we can't predict it. They're still looking for ultimate, or more primes. Turns out there's an infinity of these primes. Really weird. Which do you think is a bigger set? This one or this one? This is all natural numbers and this is a set of prime numbers. Do you think that one's a set that's bigger than another or the same size? You understand this is a subset of this?
That's more.
Yeah,
But
actually,
they're both
when you go,
infinitely long.
when you go to infinity, they're the same size. Going to infinity anyway. Okay, so now, I'm going to show you how to do square roots using the fundamental theorem of arithmetic. Okay? Hello? Okay, first, let's take a look at a prime number. So let's say I have 24. Now, this theorem says every number has a DNA made up of these characters, multiplied together. So take any number that you know will go into it, for example, a prime number. I know it's even, so 2 will go into it, correct? So this becomes 12, do you see? And that 2 goes into that as well. And that becomes 6, and you better end up with a prime number, which is 3. So the only way the DNA for 24 and no other number is 2 times 2 times 2 times 3. Do you understand? Okay. So now, if I want to take the square root of 24, the rule is you can rewrite this as 2 times 2 times 2 times 3, correct? Okay. Now, if there's nothing in the crack, you see there's no number in the crack? It's because it's so common, there's a 2 in there. We don't even put it. From there up, we do put it. So this is telling me to look for groups of 2 and pull them out. When you pull them out, they become 1. So just look, here's a group of 2. You see it? And I bring it out. So when it comes out, it becomes just one set. And then what's left inside is 2 times 3. So the simplification of square root of 24 would be 2 times the square root of 6. Now, the square root of 6, the only way to get even an estimate of it is through the calculator. It's kind of somewhat difficult to calculate, but we can do an estimate for this part. Because I'm going to do a sandwich. Here's the square root of 6, right? And this is the square root of 9, correct? I know, and this is going to be the square root of, let's say, 4. Now I got a sandwich. Okay, so I know that this is a perfect square. So remember, what does this have? 9 has a 3 times a 3. Look at that. It comes out and becomes 1, 3. So you're left with a 1 in there. Absolute value of 1 is 1. Right? So, and then we have 6, which we don't know. But we have 4, right? That can be written as 2 times 2. We look for a group of 2. Right? So that just becomes 2, right? Now I look between 2 and 3. I know that the square root of 6 is there. This is just an estimate, right? Okay? So what's it closer to? Is 6 closer to 9 or 4?
9.
4.
So I would think that instead of 2.5, you might be like 2.414, something like that. You could put it in your calculator if you want. But the reason I do that is just so that if you actually want the number, you can guesstimate, estimate by doing a sandwich on perfect squares below and above. Okay, right? So now go back to this number. So the square root of 24 will be approximately 2 times 2.414, something like that. That would be, a number that times itself should get you pretty close to 24, right? because I calculate square root of 6 over here, you see. So I'm using that as an estimate of the square root of 6. All right, let's try one more. Okay. Let me just clear that off. So suppose I want to take s squared is equal to, let's say, the summation of every observation minus its mean. I'm going to use x bar instead of mu. Square it, right? And my count has to go through the first observation all the way to the last, which is little n. And then I divide by n minus 1. Okay, is this variance or deviation?
Deviation.
Variance. If it's squared, it is variance. It's a 50-50 chance, right?
I was saying the other 50.
This, as it stands, we call this a variance. But we've been calculating deviation. That means without the 2. Agree with me? So what I'm going to do now is, in order to change this from a variance, to a deviation, I have to get rid of that little 2. So I square root it, because I know I'm looking for 2 copies. And I square root over here, do you see? But I know that s squared can be made into 2 copies. Cha-ching. That's 2 copies of s. That's looking for 2, it comes out to become 1s. Yes or no?
Yes.
So I just calculated my deviation, right? So I had to square root it, and I had to square that, but because when you square root one side, you have to square it the other. And that's why this one's equal to, let me get rid of this. Okay, so the variance, it's the same equation. It's just either with a square root or not. Xi minus x bar squared summation I equals 1 to little n divided by n minus 1. Okay, now that's called my variance. Okay, but if I want to find just the deviation, which is just the s by itself, the only way to get the s by itself is to square root it. But if you do it to one side, you got to do it to the other. So that you have the same thing, xi minus x bar squared, I equals from your first to your last, divided by n minus 1, right? But this is 2 copies of s. So I can write that as cha-ching. And I'm looking for groups of 2, come out to become 1. And there I have it, finally. S is equal to the square root of this, whatever that is. Okay. That's just so I can swap back and forth. If you want to get rid of a square, square root it, because you already got 2 copies of s. It comes out to be 1 copy of s. And if you square root one side, to be fair, the other side has to be square rooted. Yeah? Okay. So let's just take a look at, for example, if I wanted to find the square root of 8, or let's say I want to find the cube root of 8. Cube. That's okay. I use my fundamental theorem of arithmetic where I'm going to look for the prime numbers. Well, I know that 2 will go into 8, 4, right? And 2 is a prime. And this is a prime. Okay. So 8 can be written as the cube root of 2 times 2 times 2. Guess what I'm looking for groups of what? 3. No, I got 3 in the crack. That's a cube root. There's a 3 that comes out. The answer is the cube root of 8 is 2. Because 3 of them come out. Right? How about the 4th root of 16? Well, we know that the 4th root of 16 can be written. 16, 2 goes into it as 8, right? 2 goes into that, right? It's 4, 2, and 2. Notice that 4 times 4 is 16. But this is the 4th root. So I'm looking for groups of what? Huh?
4.
Ooh, I see one. When it comes out, guess what the answer is? Huh? I hear this like a muttering there. What's the answer?
2.
There you go. Does it end? No, I could have the 18th root of whatever. The main key is that you learn how to split a number up in its prime numbers. Then it's easy because you start looking for roots. Let's try just one more, 121. Let's say 122. I don't know if that's a good number or not. So I want to find the square root of it. So first I find some kind of prime number that go into it.
6.
Yeah, 6 is 12, that's 61. Is 61 prime?
Might
Yeah.
All right, that was beautiful.
So how do we estimate the square root of 61?
Yeah, but I want to show just, let's see, how about 100, 120? Okay, I know because that ends with a 0 and it's even, I could do 2 or I could do 5. 5 is a prime number. 5 goes into that twice, right? Let me see, yeah.
Yeah.
So that leaves what?
20.
20, and that goes into,
4.
but I know that 2 plus 4 is 6. And 6 is divisible by 3. That means this number is divisible by 3. 3 goes into 24?
8.
Oh, but that 2 can go into 8. So that's 4, and 2 goes in there. 2 times, look, 2's there already. And these guys running along the side here are your primes. And that is the DNA. So I can write 122, correct? As 122.
Oh, you got it.
As, I don't know. It's 122. Okay, I can write it as 2 times 2 times 2 times 3 times 5. So what am I looking for? Group
2.
2. There's nothing in the crack, it means 2, and that's the only group I can see. So the best simplification is going to be 2 times the square root of, what is that, 30? See, 2 times 5, 15 times 2?
30.
Yeah. So the answer would be that one answer would be the square root of 122 could be rewritten as 2 times the square root of 30. If I want to know an estimate of the square root of 30, I'm going to do a sandwich. So suppose I have the square root of 36, because I know that's a complete square. And then under here, let's see, I have, what, square root of 25. Correct? This can be written as what? Well, I mean, it can be written as 36, right? How can we write that? You notice that 3 plus 6 equals 9. So that means this divisible by 3, right? So that's 12. 1 plus 2 is 3, divisible by 3. 4, and 2, right? So I can write that as 2 times 2. The order doesn't matter, it's multiplication. Do you see that? Here's a group of 2, and here's a group of 3. 2. Right? So that's going to be a 2 coming out. And then it goes blue.
Well, good thing class is over then anyways, huh?
Go over the time, so.
So we're done? I can tell by movement. All right. I'm glad you're having fun.
I'm barely still awake.
Yeah, no. What's wrong here?
Well, I
Drink
just fell
coffee?
in my history class, so I was like staring at a computer screen for like 4 hours earlier today trying to get 100%. Alright, I'll be right out there, Mommy. You can just come inside with me real quick. Okay. So I was like, I'm filling my history, they do inquisitive. I'm not a history person. I'm a math person, science person. So I'm like sitting in the library, because I go to the library to make sure I
You
pass
still in
this, you know?
presenter mode.
It took me 2 hours to answer 19 questions, right?
Did you figure out how to turn it off?
Well, I know how to turn it off, but it's on presenter mode.
Oh,
And
just
then I'm
escape.
like sitting here like I feel like I'm drunk.
Right.